deviations we will use later. You will find this word actually useful. So that's why I spend more time than I normally I do. So this is also the first part shows how Einstein used this one to get general relativity. Then later we will use this, you will see very often, like what I said, how to define the parallelism gravitational waves, all the things. Okay? So last time actually we did this, last time we actually find this actually, we have two geodesics. It's called C1, C2. This actually X, A, called nu. So this actually for the tangent vector. So this actually V, A, here. There is also network. This actually psi. We have V, A equal D, X in tau. Psi equal dx, x d nu. And we also introduce a vector perpendicular to this vector is called this eta A. So eta A is defined H, A, B, psi, and H, A, B is projectile operator with B, so you can see eta A will equal 0. So this angle of the things we find this actually the geodesic deviation in terms of eta A called equal R A B C D with D with C E D. This is actually our first equation we derived. So any question about this part? Oh, okay. So now actually, like what I said, we are going to introduce a tetrad. So this actually, so we have actually this actually, this way A. So what we do actually, we just construct a small, this actually kind of like the tangent vector, the geodesic, right? So we have actually introduced, I use this parenthesis here. This actually means the vector 1 with the 4 components, right? So sometimes I use AB, sometimes I use a Greek letter. Let's use AB. So here actually, this actually called 2A, E, 3. So we consider 4-dimensional. So this actually, we simply write this E. I use alpha actually 1, alpha, the Greek letters, alpha, beta equal 1, 2, 3. The Latin letters, 0, 1, 2, 3. So we use this commands. So this actually, you can see, we just simply, this actually equal 1 E A, 2 E A, 3. So this actually the third legs. They just actually orthogonal each other, so which means if I E A alpha E B beta E A B equal delta alpha beta. This is going to be minus because we consider their space line. Okay? So this is called equation 2. And of course, we like what I said, they also orthogonal with A E. Let's call this A E A alpha equals 0. So this is called tetrad because we have actually 4 legs. y equals, this is the tangential direction of geodesics, right? Now you can see, because of this condition, you can see when alpha different from beta, those guys are some. If alpha equal beta, this actually equal unit common direction. We also know this actually VA equal 1. Then you can see I can actually in principle introduce EA. Now I call B. This simply equal E0 A E alpha A, where E0 A is an equal weight, right? So if I do this, let's call equation short, I can actually write everything here together. Then E A, let's call C E B D G A B equal. Now actually equal eta C D. Where eta actually is the Minkowski measure. Where eta C D is equal, I'm going to write this diagonal 1 minus 1 minus 1. So this actually becomes the measure. Okay? This is called the tetra form. You can see this actually, this describes we can in principle replace the metric, use tetras. Perhaps you may know, local cosmos gravity is based on the tetras. So that tetra is not a particular tetra, is Professor Aztec in 1986 introduced, called Aztec variables. This actually called Dante's tetra is actually not really vector. This called with a vector with a weight. That one you can quantize the zero. But there is actually, using this tetras, there is a more gated freedom called Lorentz transformation. For example, here I have the 4 legs, right? In principle, I can make general Lorentz transformation. Then this guy still remain orthogonal. So I still have actually eta CB here, right? But this actually, you don't need to know this one unless later you study from tetra formula, standard local quantum gravity. So far, what we need to exactly, we introduce this actually, this is what we call EA0, then tetras. So this is they have the properties at a given point P, right? So like what I said yesterday, we have not defined how we can move this actually frame along So what actually normally we do this actually, we use the one more condition we call power rate transporting. So I'm going to raise here. So we just this is the, once again, I'm drawing the picture now, the wave A is equal E0A. Now I have another 3 legs, ER plus E1A, E2A, E3A. So what I require is D tau E A alpha equal 0, right? This actually equal V A delta A E B alpha equals 0, right? This means the absolute derivative. This actually absolute derivative along geodesics, right? This is my tangential vector. Or you can write it as simply E A 0 delta A E B. Now I'm going to put a C. This is why, because when C equals 0, this is geodesic, right? When C equals 0, we have actually delta V A equals 0. So this actually, I just simply combine this one plus this one. So here you see I use a C. So A, B. Now C actually can go to 0, 1, 2, 3, right? So this actually tells us, okay, now you first introduce a tetra and point P. So then I'm going to actually transport my tetra along timeline geodesics into this direction. Why I do this is because later you want to compare with the Newtonic version, yes, that we introduced. We need to project them into actually three legs. Remember there we have only eta equal eta x, eta y, eta z. Here we have eta 0, eta 1, eta 2 equals 3, right? So now I need to actually do this kind of projection, then compare with the Newtonian theorem. Okay? So this is actually my purpose to do this. I think my notes actually I write this details. Perhaps later you can find out the properties. So then once we have this actually, we can project our EA into this actually tetra. So we eta A we have actually eta alpha, this is equal E alpha A eta. So in my notes, I explain how to write the index in the parentheses. Actually, we use the eta because space. When we write this index outside the parentheses, we use GAB. So we're actually E alpha A equals E alpha beta E beta A and E alpha alpha A equals G A B E B alpha, right? So this actually you can see index inside parentheses we use eta AB alpha beta this actually I use the third dimension. Let's see. Better we use the following. I'm going to use this is called C. This is called C. D is called D, which means this can go to 0, from 0 to 1, 1 to 3. So here actually you can also, let's say, I call C. This will give me C, right? So all of them actually the index is from 1, 0, 1 to 3. But the index in our parentheses is always rise by this guy, right? So this is a definition because we know this one actually equal the E 0 A eta A. This equal V A eta A equals 0. Okay. So this actually. Now, probably you can understand why now we use this guy orthogonal. Orthogonal, this one actually, we left only three component eta x, y, z. This actually eta x, y, z we're going to compare with the Newtonian case. Remember in the Newtonian case, we have eta A. There I didn't put a parenthesis, but there are automatically index from x, y, z. So that's why here we needed to do this operator. First introduce this tetra, then project to 1 to 3. Okay? That eta on this is 3 legs corresponding to Newtonian case eta A. Any question about this problem?
Basically, why do we need tetrads here? Means after deriving the geodesic deviation equation in terms of eta, we started using tetrads.
Yeah.
So what is the purpose?
The purpose, remember.
After this all.
Okay. Very good question. There's 2 actual purposes. First, remember in Newtonian gravity we have x, y, z. That is orthogonal, right?
Yes.
So now here, this is orthogonal.
Okay. So we want something orthogonal.
Yeah.
That's one reason.
Yeah. The second reason, in Newtonian gravity, the space is flat.
Yes.
Then, if you are in time p, important p and q, this is actually the x, where the x is always parallel transport.
Yes.
Does not change the direction, right?
Yes.
But here our space-time is curved.
Yes.
So you are moving your frames around the geodesic.
Okay.
This should be actually rotating.
Okay.
So if I still use x, y, z, your x, y is rotating.
Okay.
So that's why you see I introduce this one.
Yes.
Because if I use my x, y, z, I do not have this problem.
Okay.
I have to introduce this one, make it sure comparable with your.
Yes.
Good question. Any other question? Please feel free to ask. I like what I said. We have tutorial time. If I cannot finish, we use tutorial time.
So here we are taking time to be something absolute, right? Here we are taking the time coordinate to be something absolute. So
you
just
mean-
moving linearly in time. That's what you mean by defining it with the help of x, y, z.
X, Y, Z. So if I understand it correctly, this angle like X, Y, Z because they do not rotate. In Newtonian theory, our X, Y is not rotating. But if you simply choose X, Y, Z coordinate in curved space, this X, Y will rotate. So that's why we want to make sure in both cases there's no rotation. Because rotation can introduce gravitational field, right? Artificial. Yeah. This answer your question?
Yeah.
Okay. So then we have another, like I said, absolute time because the time tau is around geodesics. This is the proper time. This is actually test the particles moving. This is like his proper time. This again make sense, right? Yeah. Okay. Any other question?
One more.
Yeah.
The deviation equation that we had obtained in terms of the Riemannian tensor.
Yeah.
So, does that have any physical significance in the sense that it actually gives some kind of picturization?
Yeah, because you see, this like what I always said, this represents geometry, right?
Yes.
For example, let's consider Mikos. Mikos, this guy goes there,
Zero. Yeah.
right? This guy is this actually constant,
Yeah.
kind of, right? So it's parallel transport.
Yes.
But once this guy is different from it,
Yeah.
this guy is actually, later you will see, there is some theorem. Hawking parallel theorem exactly something like this, not exactly, but they use also this kind of behavior, expansions.
Yeah.
So then you can see the curvature always make, if I consider a circle, let's say, a circle on this floor.
Yes.
When gravitational field passes through a circle will deform.
Yeah.
Normally actually it's
So
converging.
this property that you're talking about, that when gravitational wave passes through a circle, it will deform it. Can it be shown using this equation?
Yeah, I'm going to show you exactly later.
Okay.
So I will use this to define gravitational wave.
Okay.
I will do this exactly. That's why I have been emphasizing so much geodesic deviations. We will frequently use this.
Yeah.
Yeah. Okay.
Thank you, sir.
Okay. Any other question? Then you can see now if I multiply this guy. Do we have color one? Okay. No problem. So I'm going to erase here. Remember, this is detail. This is like a constant, right? So if I use this d squares eta a, d tau squares e a alpha. This guy is a constant, so I can simply d squares eta a e alpha a. Correct? Because here, this perfect. So I can just put it. Why I do this? Remember, this angle exactly my eta alpha.
Yeah.
Right? So this angle will give me the d squares eta alpha d tau squares. This will equal R A B C D VA actually equal E B 0 E C 0 multiply eta D. Eta D, I think, did I have eta D? Eta D actually you can write like this. Where eta D equal E D beta eta. Beta. So in my notes, I prove this explicitly. You can actually easily to understand. If you do not understand this part, often come to the tutorial asking this. I will actually skip this part. Just simply multiply eta d. Eta d actually equal E d beta eta beta, right? You see why I do this? Because I want everything just the eta alpha. Here is eta b, right? So then you can see all we have is the following: d squares eta alpha d tau squares plus, I will take this on the other side, plus k alpha beta eta beta equals 0 for becomes the actual tetracomponent. This has physical meaning. This is called tidal forces. So, for example, because like what I said, this is moving along timeline geodesics. So now, if you project a Riemann tensor component, normally a Riemann tensor component has no direct physical meaning because the coordinate can be chosen arbitrarily, right? But this one is different because it's time-like test particles moving along time-like geodesics. They build a tensor frame, project a Riemann tensor into this frame. Now, each component represents tidal forces. You can really feel this. This is a physical component. Okay? So we have this. This is the definition. Let's see, this equations. Do you remember? I think this will be 6. Let's call 7. So this actually, now you can see it's quite similar to the GIAN case, the Newtonian case. Newtonian case, A plus chi AB eta B equals 0. But now this AB equal 1, 2, 3, right? So you can see now my alpha beta exactly equals. So this is my chi AB, right? Where actually chi AB, this actually, let's call this called Newton. Huh? I'm going to put actually this to be different from this one. The Newtonian case, this guy is defined like minus dA dB phi. So in the vacuum case, the Newtonian gravity is chi I A equal 4 pi G rho, right? So if my rho equals 0, vacuum case, so this actually guys equals 0, right? Which means if I consider analogous to the Newtonian case, my K alpha beta should be 0. Okay? Now I'm going to actually use several arguments to show how we can transform the Newtonian vacuum case to vacuum case in Einstein theorem. There are several arguments. This argument is universal. When you do some research, you can use it often. So I think for you guys, especially some of you already doing some faculties here, so also postdocs, I think when you learn something, try to always use this. Learn something, not a purpose. Really learn something use, especially grad students or postdocs. So I always emphasize to my students, you have to be a student, because if you are not a student, you do not know how to apply. A student does not mean successful grad student. Successful means how to apply what you learn, right? You have two steps. You must be a student, otherwise you cannot, it's not easy to apply what you learn. You really understand the problem very well, then apply to your research. So this actually, I'm going to use several arguments to see actually, later, this is our goal. This is the Ricci tensor. This guy is equal, or equal this one. I'm going to use several arguments to actually get that point. Called zero vacuum should correspond to alpha equal 0, right? So here, which means I have R, A, B, C, D, E, A, alpha, E, 0, B, E, 0, C, E, D, alpha. This should be 0. Correct? Now, because this is a sum equals 0. So sum equals 0 does not mean this guy is equal to 0, right? So of course, sum equal, if each term equals 0, sum always 0. But sum equals 0 does not mean this coefficient equals 0. So I'm going to argue this actually implements this guy. Okay? So this actually was my goal. So to do this actually, we can always choose a coordinate, let's say on one point. So let's say on P, we choose so that E, B, A equal dark A, B. So this angle coordinate I use a star. This angle A, B equals 0, 1, 2, 3. Then you immediately know this angle, if I take a equals, this b equals 0. So this angle EA has only one component, right? So which means actually it's exactly on my time direction, right? So if I take actual x, y, z, for example, x, a equals t, x, y, z. So if I take a b equal 1, the only component is E1, A is 1, 1. Otherwise equals 0, right? That means it's a tangential direction along x direction. The same thing he can do this. This is only particular choice on the point P. So in the curved space-time, I can always choose this. And the point on my tetra has this properties, right? If this is the case, then you can say, now, what about this actually R, A, B, C, D, E, A, alpha, E, D, 0, E, 0, C, E, D, alpha. This is where R, A, B, C, D. This is actually equal delta alpha A right here. Yeah, this is where delta 0 D, delta 0 C, delta D alpha. So this angle, this is in particular point. So I just use stars. So this angle, then you can see this will equal alpha 0,
स्टूडेंट को
0,
मूवी कराते
alpha.
हैं ना
This
बीच
is
बीच में
equal 0, right? But R 0, 0, 0, 0 equals 0. Because the Riemann tensor is undismensional with this guy. So this actually, if they are the same, this is 0. So I can, this apply to this one. Then, now you can see this from x, y, z, right? I can generalize this because of project, I can use a from a 0, x, y, z, or t, x, y, z. So this actually give me a equal 0. But we know this R A 0A equal minus R A 0. So this actually is a undismeasured. I change this one. So this actually will give me, remember this A, I'm actually, I pull back my weight. So this will give me R A C A D we C we D, right? Because this is, I use actually weight, the only delta one, this guy is equal 0, right? So this actually we C equal E C 0 equals delta C 0, correct? Pull back, use this one. Why do I do this? Because this anchor, by definition, this guy is equal R C D we C we D. Okay? This is the argument the following. I first choose a point P. Then make a coordinate transformation so that actually the tetra take only E AB equals delta AB. That point. Okay, I can always do this. Once I do this, actually, I most with from Newtonian theory, this alpha should be 0. Then I get this expression, right? So I get this expression, but this guy is always 0. So I just put another term, then become this one. This is still in the particular coordinates, and that specific point P, right? So be careful with this argument. So we get this one, or we have this anchor equal 0. This again, in particular case, right? And point P. Now, I'm using the following. This anchor true and point P. Correct? Did I say P is the which point? That P can be in China, can be here in Raleigh, right? Can be actually in Waco, Texas. I'm from Waco, Texas. So it can be any, right? So if actually this P, for any P is true, then we should have A, B, V, A, V, B should be equal to 0 for any given P. So this is actually very important argument. When you do some research, you will use this kind of ideas very often. Because I just pick a point, P, then this allow me to choose this coordinates so that E, A, B equal delta AB. So I can always do this. But the problem is this P can be any point in the manifold, right? So then this must be true. So please pay attention on the argument, because this is a true for any given point. So this will be true over the full manifold, right? Now, I also use another argument. So we consider our test particles over the manifold with the only thing our assumption is timeline. How many timeline test particles? Infinite, right? You can have as many as you could. So in principle, each point I can pass one timeline geodesics. So if this is true for any given way, this must be true only for one RAB equals 0. Right? So my actual second argument is since equations start is true for any given C1. C1 is timeline geodesic. True. Only one RAB equals 0. Okay? So this is actually the vacuum. Right? So if you read, like what I said, if you read the history of general relativity, Einstein got something different from this one. So lots of historians said like, he was lucky because he proposed this one, something different from this one in 1914. Then immediately, before 1914, I forget the exact time, because in 1914, there's a team went to Russia to observe the eclipse, solar eclipse, to measure the shadows. This is exactly from this is the wrong theory. Then he calculated the angles. So actually he was likely to send their time World War I. So the actual team went to Russia. Russia thought they was actually German spies. So they just captured them, put them into jail. So they didn't actually measure this one. Then after that he realized the equation what he proposed was not correct. This is a correct. So that's why they sent the second team in 1919. So one team went to Brazil, Costa Rica, another went to South Africa. So the South Africa team actually, they took the photo, they found this exactly 43 seconds Einstein theory per day. This actually the Newtonian theory actually cannot give this one. You know the whole story. But unfortunately, Brazil actually was clouded. The film, the negative was actually exploded. They didn't actually use that. So this is the whole story. This is RAB equals 0. It's a vacuum case, right? Yeah. Any question about this part? You see, actually from the very beginning, actually we can learn on this and come back to actually geodesic deviation. They try to project this actually into the tetrad timeline, and then we get analog. We get the motivated by Newtonian theory, then get this one. Why we use motivated by Newtonian theory? Yeah, my question is why we have to consider Newtonian theory here? Because you just simply propose a new theory. What's the fifth principle? The corresponding principle, right? What's the corresponding principle? Einstein's theory needed to reduce Newtonian theory. When velocity is very low, when the gravitational field is weak. Which means Newtonian theory is correct. But you have to actually apply to the correct domain, right? Which is actually low velocity, weak field. So this is actually why we use this one, right? This is actually his principles, correct? Maybe when he proposed Hitler's theory, he didn't explicitly write, okay, this is my fifth principle, I got it there. But on these times later, people try to understand the logic of here, related to things. So this is actually the fifth principle. There's a correspondence. In the weak field, we needed to get a Newtonian theory. So that's why we want to actually first motivate from Newtonian theory, then to this case. Later we will derive Newtonian theory explicitly. Okay? So this is actually the one case. Now, how do we get something actually beyond this one? Before we get this one, I'm going to actually write this one. You know, this guy is called Ricci scale equals GAB RAB. So since the RAB equals 0, this R also 0, right? So this actually this one. Now we have a GAB, the Einstein tangent equal RAB minus 1/2 GAB R. So this actually RAB equals 0. So this actually you can see RAB equals 0, the equivalent to GAB equals. That's called equal to 9, right? So this vacuum case, I'm going to use another principle that we just mentioned to generalize this to copying with the metal. Okay? So please try to pay attention to the logical here. We know the matter distribution by described by PAB. PAB, right? So it's called energy momentum tensor. Classically, AB dx A equals 0, right? This is conservation law, correct? So now, what's the principle? General covariance, not general covariance. When we generalize this to, we just replace partial derivative by covariant derivative. So I'm going to write this. That's better to use this one. So this will be 0, right? We do not put a Riemann tensor here. So this is the case, right? Now you can see we have to have this property. On the other hand, we know delta A G A B equals 0. This can be get from GIAN identities, right? So we also know clearly this A G A B equals 0, right? So if you put this shirt together, let me see, I'm going to put on C, T, A, B equals 0. This is constant. So if this is true, then I have, sorry, this is going to be G. Right? So I should have something like this. So this is my guessing, right? So I can define this like my lambda GAB minus lambda GAB. This actually, I just simply use color TAB. This is a famous Einstein equation. Right? You see now we use one of the 5 principles to get here. So there's a lot of activities here, right? You can see this equals 0. What's happening if I have quantities? You can always plug one here, right? So, but this one I can always observe this one. This would be something like energy momentum tensor. So, although we do the 100. So that one you're familiar. This actually the Einstein cosmological constant. It was so regular to put it here. Instead of this actually totally destroyed, it's actually 0. But now we know we need this guy to explain our universe expanding. So, any question about this part? So this actual constant, we're actually getting this constant. We're using Newtonian approximation to find this constant. So this constant, when we come to cosmology, we need this one. We needed this one. The problem is the following. So the particle physicists, if they can calculate our vacuum energy, they find vacuum energy exactly this form. So if you use quantum field theory in curved space, then you find this actually the vacuum energy I call P lambda A B equal rho lambda U A U B. Sorry, this would be. I have actually theory for lambda from KFT. But now this actually the problem is following. This actually about 10 to 100 shorter row line what we need over there. So how we can get this one? You can actually use quantum field to calculate vacuum energy. Because the vacuum energy should be like on the Planck scale, you expect this guy is on the Planck scale, right? Because the quantum girl. Now, though, what they always find this word extremely small. This the difference is 124 hours. Okay? So then this equation equation. So if we do not understand, if we learn the quantum field, so that's fine. We say, okay, Einstein just introduce the lambda-like constant. You just determine by observation, like speed of light. Whenever this constant comes from, that's fine. Einstein said, okay, I didn't actually consider quantum phase. I just my optional constant. I just use my argument again. So how big is this? Experimentalists are going to determine, like speed of light. Yeah. Go ahead.
So how is that lambda interpreted as vacuum energy in QFT?
Yeah, good. So now the particle physicist said, okay, I'm not quantum physics on the curved space. I can calculate my expectation values of the ground state. Your energy momentum tensor. You can quantize. You have a classical one, right? Then you promote the operator. Then you consider the expectation values, right? Whereas this guy's giving cosmological constant. That cosmological constant is this one, which is 123 orders larger than what we need. Okay? This is actually the problem. This is called cosmological constant problem. So from Einstein's point of view, this is an arbitrary constant. From particle physicist's point of view, I could theoretically calculate this actually, lambda, and find avoidance. Like what I said, this actually should be prime scale. Why? Because you consider quantum gravity. This is automatic. This actually is exactly 120 orders. So far we did not know how to resolve the problem. Either our understanding of quantum field theory in curved space is incorrect or incomplete, or we do not understand the vacuum. Dirac said, if we understood vacuum, we understood quantum mechanics. Right? So here, somebody says, if we understand vacuum, we understand quantum gravity. So that's actually the big challenge so far we have. Any questions on this part? So this actually, I just want to give you actually the general flavor of how Einstein had lead him to get the equation. But the really important thing for you to understand, just try to understand the argument, logical argument. So when you do some research, whatever kind of research you are going to get, can you actually follow some kind of argument like this? Or if Einstein didn't discover his general theory 100 years ago, can you discover that? Right? So this is a question I would like you guys think about this. You know, Einstein 25 years old, right? When he proposes. This is exactly something like your age. Any question on this part? So this is actually the theory of the Einstein theory. The whole thing actually to try to understand the implication of this one. So like what I said before, observation of gravitational waves, we was mainly actually restricted to the weak field regime. Weak field regime means actually, for example, when in our solar system, this is actually weak field. In the solar system, most experimental you can use actually tensor. That's perfect okay. You do not need to use Einstein theory. But one thing we daily use Einstein theory is our cell phone, right? So our cell phone has to correct every 2 minutes. Otherwise, we'll get big errors. You cannot really use our cell phone. So this actually is the GIAN effect. Other than this actually, really, little bit actually, it's almost irrelevant to our development, right? Yep.
So considering this lambda city model actually gives rise to this cosmological problem. So according to you, how well is this scalar field theory trying to compensate for this cosmological problem?
So can you repeat that again? Yeah.
So
Okay.
considering this lambda city model actually gives rise to this cosmological problem. So how well do you think these scalar field models are actually there to compensate for this cosmological problem? Like it scales down or like the slope of it to the -6 and then you get the cosmological problem. And there are lots of scalar field theories that we consider potential and then they kind of tries to resolve this cosmological problem. So according to you, how well is that these scalar field theories approachable or was there a valid theory for this compensation?
Yeah, okay, thank you. That's a very big question. So you heard his question, I'm going to repeat. Now the standard model, the standard model, this name actually changed a lot. The current standard model, which means the lambda CD model. Lambda CD model actually is we consider cosmological standard model, unless from point of view Einstein theory. Now his question is, how do I consider this? This is a very big question, very good question. But personally, I think that lambda city model, there are only 6 parameters. So you can very precisely determine all of them. If you look back to the history of science, we always start something simple. Then we go to only when we reach the step, the simple model cannot explain the things that we propose. More complicated, like Newtonian theory, right? Einstein theory might complicated than Newtonian theory. I think now perhaps this should be reached at a point, lambda city model maybe needed to be revised. How, in which way, really depend on you guys. So I think that this is really one of the best time if you look at the history. But actually, if you use supernova type 1A or local measurement, even not real local measurement, then you will find this edge node is about 6, 7 plus minus. Now this actually is sigma already bigger than 5. So if you're familiar with the experiment, normally we say when we have 5 sigma deviations from observation, then we have new discovery, right? So here, if you combine all the things, the CMB, this is from CMB, the lambda city model, the difference as you know from locally or other observations already more than sigma. Why we do not declare as a new discovery? Because the problem is so complicated. So when we measure from the type of 1A supernovas, there are lots of systematic errors we may not know. So although we get a 5 sigma, this is 5 sigma, maybe there's some part we do not understand very well. There's some people actually think so. But if you talk with actually people who are doing supernova type of 1 measurement, I have a young colleague just joined Bayer this year. He actually has been working with the Nobel 2 groups who observe this actually acceleration. He said, no, we just cross our head. I have been working on this for more than 10 years. We didn't find any system of error which can explain this 5 signal. We do not know. So this really, when talking to him, he strongly believes there's five signals there. Or either cosmological model is very incorrect, right? Or you have some systematical errors. So this is actually another big challenge in cosmology. So we do not know. So this is actually the big errors. Of course, you have gravitational waves, you have observations. I think that this parameter, I consider the best time to do growth. Another thing, we have 4 different forces. All the 3 forces are quantized except the growth. So the standard model is perfect. Okay, Higgs field, Higgs particle was discovered 10 years ago, right? So what are you going to do? You cannot sit on here. So you just automatically come to a lot of particles tend to grow because you want to quantize growth. So this goes to the 0. Okay. So this is actually the time I think for you guys to work on this. Okay, any other questions? These are my personal point. This is accurate. So, any other questions? Okay, if you do not have a question, let's turn to lecture 3. Lecture 3, the spherical symmetry. So, I think my notes actually, I wrote my notes using Kelly vectors. This is a precise way actually how to define spherical symmetry. You can see, for example, if I give me a function which is x, y, z. So from x, y, z, it's difficult to see the spherical symmetry, right? So what do you do actually? You just use this x equal r, or say use the spherical coordinate function. So okay, I get a fr. So this is spherical symmetry, right? But you remember in general relativity, you can choose any coordinate. Classically, this r equal sin theta cosine phi, y equal r sin theta sin phi, z equal r cosine theta. But you are not so sure if this still works actually in curved space, right? Because you do not know if your coordinate is really x, y is related exactly spherical coordinate here. Because you notice the x, y, z, but it's not necessarily Cartesian coordinate, right? So what do? You use Kelly vectors. Kelly vectors actually uniquely determine the properties. Okay. So I think in my notes actually we did it. I just explained in details, but. Today I'm going to actually do another very quickly, very powerful argument we call unbinding. Unbinding means actually I am binding, let's say, this table, the 2-dimensional plane. I'm going to put this 2-dimensional plane into 3 dimensions to see what is the geometry, how this looks like. Use this argument that you can easily generate to other cases. This is, of course, not so accurate, but it's powerful. For example, one day I want to start playing gravitational wave. I can start from my Nicole space with the plane symmetry and bind it into 3 dimensions. I get a plane symmetry. I can consider 2-dimensional spheres and bind it into 4 dimensions. I get a spherical symmetric space-time. Then my question is, what's happening if when you want to start high-dimensional space? Can you combine this like 2 spheres that's to 5 dimensions? My answer, yes, you can. Very easy. I will just show you how to do this. So if I have a plane 2-dimensional, can I combine this into 5, 10? You can do any dimension. You can do using this called combining method. Okay. This is actually quick. Also, you get a similar result. If you want to do this more precisely using kind of work you can do, this is my notes I explain step by step until how to define static, how to define stationary, how to define spherical symmetry. That's actually really the way you can define. But today I'm going to do something different. So, lecture 3, the spherical line. Measure. So let's start from, let's say, Minkowski. So Minkowski space, we have ds squared equal let's say dt squared minus dx squared minus dy squared minus dz squared. So Minkowski space has all the symmetries, 10 categories. For the dimensional case, you can prove the maximum symmetry is Minkowski space. This contains 10 categories. You cannot build any space in four-dimensional which has more than 10 categories. This is only maximum symmetric space. That's why if you cut in one way, you get a plane. If you cut another way, you get a spherical symmetry. If you cut it different, you get a cylindrical symmetry. Why? Because this space has maximum symmetries. Depending on how you cut the two-dimensional surface, you can get any kind of symmetry you want. It's a maximum symmetry. 10 categories. Okay? So I'm going to show you how we can make a cut with a spherical symmetry. You know this angle, if we do r equal sin theta cosine phi, y equal r sin theta sin phi, z equal r cosine theta. So this angle, the z, y, x, right? So I have vector, this is the theta, this is the phi angle, this is r, right? So this angle, the meaning. So plug this into this expression, I have ds squared equal dt squared minus dr squared plus r squared d squared theta. Let's do this. D omega squared d omega squared equals d theta squared plus you see, I just write this. This is called S2 symmetry, right?
Sir, it's the negative, I think, before R square.
Oh, yeah, you're right. Thank you. Okay, so this is negative. So we have like this is called S2 symmetry. So you have actually a sphere z x y. This angle gives us on this surface with the r, theta phi is the coordinates, right? So my angle theta belongs to 0 pi, phi belongs to 0 2 pi, right? So this is cover whole sphere. This is have topology, this too. This is called spherical symmetry, right? Now, this is because I'm going to combine this angle into four space with a spherical symmetry. So suppose my metric let's say ds square equals something, and this is GAB dxa dxb. Now I use actually x0 equals t, x1 equals r, x2 equals theta, x3 equals phi. Okay? So this is my GAB dxa dxb. So when I restrict my to the ds when t equal constant t0, I equal r0, this 0 is constant, I should get something like minus d squared, which is a function of t r, but now tr becomes not multiplies d squared. Okay. Right? This is my maximum because when t equal constant, you see here? Can consider the product. T equal constant, R equal constant, R not. Normally this product can be depend on time, but our universe is expanding, right? So when I put t equal constant, R equal constant, I get equal some constant which depend on t0 and r0 multiply my two-dimensional spherical metric. This guy is precisely defined as two symmetry, right? So now I'm moving back to this. I'm moving back. So if I know this one, I go back, come to here, then you can see my metric should have ds squared equal GAB dxa dxb plus d squared tr d squared omega, where a b equal t r. This is called embedding. I have a start from a two-dimensional surface which has spherical symmetry. I'm going to put it into four dimensions, like my table. My table has two-dimensional plane. I'm going to put it 0. But I also have time arriving, right? My time actually is included here. My x is included here. Here actually on my x, this is actually my t, z, here only my plane. Plane is dx squared plus dy squared. Later I will come to this. This is called hyper-embedded S2 spheres to four dimensions. Then here the b, the only thing, AB is a function of t, A equal t and r. And G, AB must be only functions t, r. Let's see, this is 5, this is 6. Can you see why? Suppose this is not the case, let's say this depends on theta. Do I have spherical symmetry? I do not have, right? If it depends on phi, I do not have spherical symmetry either. So this tells us, okay, if you have two-dimensional spheres, when I put embed into four dimensions, this is always the case. Right? So you see how easy? Okay? Now, what about 5 dimensions? So let's say I have a 5 dimension, but I still have a 2-dimensional sphere. I'm going to embed this into 5 dimensions. Let's say the 5 dimensions will be t, how can I say, r rho, right? Plus theta phi. Okay? So this you can call t x0, x1, x2. Let's do this. The 5 dimensions, A becomes x0, x1, x2, so 5, right? Then you can see now ds5 equal GAB, dxa, dxb plus d squared, which is a function of x1, x2, d omega. Then a, b equal 0, 1, 2, and g, a, b depend on only x0, x1, x2. Right? You see how powerful this is in mining? So if I want to work a 5-dimensional space-time, now I want to have spherical symmetry. Once I get more than this. Okay? So you see, I have 3 extra dimensions. Right? So if you use Kelvin vectors, how many Kelvin vectors are you going to introduce in high dimension? So this is actually very powerful, very simple, right? Well, yeah.
So in this, then we have 4 spatial coordinates.
Yeah.
We're talking about reducing 4 spatial coordinates.
Yeah.
And not time coordinates.
Exactly, yeah. So in principle, you can say I have actually, let's see here, I can have, let's say, another, this actually can be used space timeline. But the embedding does not care if space line, how many timeline space line currents. Of course, we know for example, normally we have only 1 time. If you have 2 times, the series always has ghost. So there's some powerful series. Any space time with 2 times, actually you have ghosts. So that's why 5 dimensions. Okay? You have 1 time, 3, yeah. Okay, very good. Any question? What about 6 dimensions? The same, right? Here this AB becomes 1/3. Still have 100 dimension. 2 plus 98 extra dimensions, right? You can control any. So this is what we call a mining. Very powerful, very simple measure, right? So now this actually spherical symmetry in man. What about if I have a, let's say, plane symmetry? When we say plane symmetries, let's say ds squared equal minus, plus dt squared minus dx squared minus dy squared minus dz squared, right? The plane symmetry, this one, if I put p equal constant, my z equal constant, this will give me minus dx squared plus dy squared. This is 2 plane, right? So xy, let's see, from minus to plus infinity, this covers the whole plane, right? So this is because this actually has a plane symmetry, xy. How do we combine this to 4 dimensions? Right? So this is all the functions here. This is called plane symmetry. So this actually you combine it into a 4 dimension. Now, how do we do 5 dimension? This is just simply plus 1. 6 dimension, plus 4. 7 dimension, plus 5. But this part remains the same. Okay? You see, this is actually a very powerful measure of how we get actually symmetries without considering cutting work. Okay, this is actually for the extra dimensions here, but remember, this coefficient cannot depend on x, y. This only depends on qz. Otherwise, you do not have plane symmetry like a spherical symmetric case. Okay. What about cylindrical symmetry? You can do something similar, right? So this is actually very simple, very powerful way to actually consider different symmetry of space-time. So whether let's say rotation stationary, you can do something similar. You can consider combining 4 dimensions and 5 dimensions whenever you want. Okay? Any question about this part? So I will actually, like what I said, really define the space-time rigorously. You need to find the cutting reference. This is a mathematical process, but this always gives the same result. It's not simple, straightforward. Okay, so now let's actually come back to the 4-dimensional spherical symmetry. ds squared equals GAB TR dxa dxv plus, this will be minus d squared TR d squared omega. This is the most general spherical symmetric case, right? Here xa equal TR, right? This actually allows me to make the following transformations. P equal F T prime R prime, R equal G T bar R bar. This guy's operator functions, right? So if I do this transformation, I still have the same form, or not change, right? So this like what I said, still spherical symmetry. But this is operator functions. Okay. I will not prove this. If you want, you can make this transformation by properly choosing. So using this freedom, F and G, how many? We have 2 degrees of freedom, right? I'm using those 2. We said actually, not to choose. This is 2 conditions, right? 2 functions. So, in principle, I can always do this. So if you do not believe me, try make quantum transformation, put in this condition, you will get actually 2 equations, right? Just solve this equation. So then you can see this will lead to ds squared equals g t dt squared plus g r dr squared minus r squared d omega squared. Right? But we know this guy is going to be always a positive, right? So I introduce another one called nu tr dt squared. This is always a negative. So I'm going to write e lambda tr dr squared minus r squared t squared omega. So this is a spherical symmetrical space-time with choosing the 2-degree firm like this. Of course, you can choose different again, right? Later we'll select one we consider from the Frankenstein. And in the Frankenstein coordinates, we'll choose not this one. We'll choose like a GRR equals 0. And we just like only TTTR component. That's fine. This anchor different gate, right? But this anchor is a gate from a Wang to use. Next class, we want to get a vacuum solution. You see here? So I just escape all the anchor, consider Cannon vector, using minus to consider anchor for symmetry. So you can actually easily generalize to other symmetries or with any extra dimensions whenever you want. Okay. This anchor is simple and powerful ways one can consider. I think about how so. Yeah.
So we have a tea break, then we will meet at 11:30.
Okay, good.